Hi everyone, so we've got our M1 example problems here. I can't remember if we talked in detail about the scale pan last time. Can't remember, so I don't think we did. Let's go for it then. So what do we do when we've got a lift problem like this? I don't think we've done anything like this before, because I'm doing the video again and I'm a bit lost on where I am. So I'll just pretend, I assume we haven't. So we've got what's called a light scale pan, which, as you can see, is kind of like a hollow, in buildings where they just these bits here are kind of wires or whatever, and then you've got a wooden base, and then some crane is lifting some cargo. So a light scale pan means zero mass, so you don't need to worry about the weight of the lift itself. So it's attached to a vertical light inextensible string. We know what that means. Zero mass and inextensible means that the acceleration and the tension is constant throughout the whole string. The scale pan carries two masses A and B. The mass A is 400 grams, but we know we don't work in grams, so we'll cross that out straight away. That's 0.4 kilos, and this is 0.6 kilos, yeah, for A and B. Saying A rests on top of B as shown in the diagram. The scale pan is raised vertically using the string with acceleration 0.5 meters per second squared. So normally I say just race off, but I don't want you to do that. I want you to follow this video because we haven't done things like this before. So it's raised vertically, so everything's accelerating with 0.5 meters per second squared. And it asks us to find the tension in the string. So you can see here on the diagram that this has a tension. But what isn't clear straight away is kind of, well, what is the question asking? Well, the string is carrying the whole lift and all of its cargo, isn't it? It has to take everything. So you can treat this as a single particle. Can you see? A particle that's moving as one with 0.5 meters per second acceleration going up. And you can see that the total weight this thing is carrying is 0.4 plus 0.6 g. So this is just g. That's all the string doesn't really care about how many objects are within the lift, does it? It's still got to hoik everything up. So now we can resolve as normal. So to find the tension, we resolve up T minus G. So force going up is T, G's going down, is total mass, which is 1, times acceleration, which is 0.5. So we've got T equals G plus 0.5, which is 10.3 newtons for SF, because we've used G. So there we go. Happy with that, I hope. Part B. Find the force exerted on mass B by mass A. So this is something people do get in a bit of a tiz about. But if we think about it kind of logically, the force exerted on mass B by mass A. So if we treat B like the table, that's essentially what's happening. A is resting on B, isn't it? And therefore B, the force exerted on mass B by mass A, is going to be the weight of A, isn't it? The weight A is acting on B, therefore B has to produce a normal reaction in order for this thing not to fall through the floor. So this particle is A, which is on B. B has to deal with a weight of 0.4 g, doesn't it? If it wasn't able to produce a normal reaction sufficient enough, A would just fall straight through it and it would go, you know, and we know that that doesn't happen. We know B can support A's weight. Everything is still moving up with acceleration 0.5. So can you see, in a sense, when you see a problem like that, it can just be reduced down to, well, B is a table, B is a flat surface, or B is a surface that A is moving upon. So now we're just isolating at A, aren't we? So at A, we're resolving up. The force going up is our normal reaction, or that force exerted on B by A. So, and the force going down is 0.4 g, and that equals total mass, which is 0.4. Remember, A is the mass in question here, and our A is 0.5. So we know that that force then, RB, is going to be zero point 0.4 times zero point 0.5, so zero point 0.4 times zero point 0.5 plus 0.4 times 9.8. So that is 4.12 newtons to free SF again. You see? Okay, in part C, this isn't going to take very long because it says find the force exerted on mass B by the scale pan. So let's think about it again. The scale pan is now the surface. So scale pan is the surface. Particle B is resting on the scale pan. Well, not resting, it's not in equilibrium. But also particle A is as well. So the scale pan has to take both B and A's weight, and it has to produce its own normal reaction, otherwise B and A are going to fall through the scale pan floor. So what weight does this thing have to put up with? Well, it's zero point 0.4 plus 0.6 g, so that's just g. And it's still accelerating up, isn't it, with zero point 0.5. So can you see, actually, this is exactly the same as question A, isn't it? It's what forces are acting on the scale pan, what normal reaction is going to be in place. Well, it's going to be exactly the same as the tension. So I know straight away RB, just like before, so I'm not sure what happened there. RB is the force going up, so we're resolving up, minus G equals total weight 1 times zero point 0.5. So therefore RB is the same, sorry, RS, because it's a scale pan, so we'll call that RS. RS is going to be G plus zero point 0.5, so 10.3 newtons to free SF again. You see? Okay. Hopefully that's cleared up that type of problem then. Right, next example. So two particles A and B are connected by a light inextensible string. Particle A lies on a rough horizontal table from a smooth pulley, hands freely. Okay, so here we go, horizontal table. So particle A, let's circle that one. Particle B, we've got our pulley here. I'll call that P. A has a weight of 0.4 g, so hopefully you're sketching this out as well at the same time as me. So there's a normal reaction RA, it's connected to the pulley, there's a tension there, there's a tension there, there's our particle B, so there's a tension there, separate your system, tension there. Remember we talked about the weight, just actually draw the arrows for the weight. I don't know why people aren't doing that, it's really annoying. Okay, and it's telling us it's on a rough table, and it's 4.5 meters away from the pulley, so there's 4.5 meters there. And it's telling us that the other one is 0.5 meters from the ground, so we've got that. The coefficient of friction between A and the table is 0.2, so there we go. Friction is 0.2 times by RA. Okay, the system is released from rest, so therefore everything accelerates down here and across here. So part A, find the acceleration. We're going to do a few things on here. We're also going to learn how to find the force acting on the pulley. Okay, so that's going to be part D. But for part A, find the acceleration of the system. Everything's resolving down, so we should be getting used to this now. What force is going down? So resolving down, total force going down. You can see from the diagram is 0.8 g. What's resisting it? Well, the friction at A is resisting this thing, so 0.2 r. And this equals, because we're doing F equals ma, our total mass is our 0.8 plus our 0.4, so this is 1.2. And then we've got our A, which we don't know. We need to know what this RA is though, don't we? So the only way to do that is to resolve at A. So the force going up here, because remember this RA and this weight here has no impact whatsoever on lateral movement, i.e. side to side movement. So we've got force going up is RA, force going down is 0.4 G, and it's in equilibrium, isn't it? It's not bouncing up and down on that table. So we know RA is 0.4 G. And we can sub that into our equation here. So 0.8g minus 0.4g, which is our RA, times by 0.2 equals 1.2a. So therefore A equals all that lot divided by 1.2. So hopefully you're using your calculator as well. And again, if you disagree with me, give me a shout. So I've got A as being 5.88 meters per second squared to 3SF. Wicked. So assuming that's correct, doing a quick scan of it, it looks okay, but you guys might have spotted something not quite right, but let's assume it is okay then. Let's do part B. So it's saying find the time taken that this thing reaches the ground. So when this thing reaches the ground, it's got to travel 0.5 meters, doesn't it, for B to hit the ground. So we're going to have to use suvat, aren't we? So 0.5 distance, it starts from rest, don't know what V is. We know what A is, we just worked that out, so that's 5.88. And the time, that's what we're trying to find, and everything's moving down. So time taken for B, so we don't care what V is. We've got S equals UT plus half AT squared, and therefore 0.5 is 0 plus half a 5.88 times T squared. So T must be, again, calculators out. So 0.5 divided by the 0.5 is 1 divided by the 5.88, square root that, and you get 0.412 seconds to 3SF. And it would be plus or minus, wouldn't it? But obviously time can't be negative. So that's part B done. Part C, find the total distance travelled by A before it comes to rest. Well, once we need to think about this in a few stages, don't we? Because once the particle hits the ground, particle B, A is still going to be moving, but it's got to fight friction though, hasn't it? So, like I say, it's a two-stage operation. So we need to know the speed that B is going to hit the ground, because that's when A is going to be no longer pulled by B, and it's going to be subject to deceleration. So when B hits ground, what's the speed, in other words? So when B hits ground, we can use our old suvat table here, except we're looking for V equals U plus AT. We could do it that way, but I don't want to use T answer because that could be wrong. So you don't want to compound your kind of errors. So if we use the information where we know we can guarantee its correctness, but obviously if our initial acceleration was wrong from the start of the question, then everything is going to be wrong. So when it hits the ground, V is going to be, if I whack this in, so 2 times 5.88 times 0.5, all square rooted, you get 7 square root of 3 times over 5. So that's V there. And then we probably need a new diagram, because that's going to be the starting velocity of A before it starts to slow down. So on a new diagram, you can see A is moving. They've still got friction, which is 0.2 R, which is RA. RA still hasn't changed, but there's nothing pulling it to the right anymore. So if I was to resolve to the right, because I need to know the deceleration, nothing's going to the right. Only 0.2 RA is going to the left, and we know that RA, sorry, is 0.4 G, and this is our mass of movement at the moment, so that's 0.4 A. So therefore, A is going to be minus 0.2 times blah, 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 so minus 1.96 meters per second squared. Therefore, we can use suvat to finish this off. So suvat because it wants to know the total distance moved. So we're going across. S, we don't know. U was our starting values, which was 7 root 3 over 5, which we found here. V is 0, because that's when it's going to stop. Minus 1.96, and time. Don't care about time. V squared equals U squared plus 2AS then, and therefore 0 is 7 root 3 over 5 all squared, plus 2 lots of minus 1.96 S. So if you rearrange that, you should get S equals 7 root 3 divided by 5 all squared, divided by 2, 1.96, should get 3 over 2. So, but remember what the question said? The question said total distance. So total distance traveled by A is going to be that 3 over 2, but plus the 0.5 it started with, so 2 meters. Okay? Finally, we could finish off by finding the force on the pulley. So this is an extra bit of the question. So so this will be part D. Find force on the pulley when the two particles are in place. So I'm going to do this on this next slide. So we know that our system was made up of tension, tension like that, didn't we? And we closed it off, going from the pulley towards the other particles like so, didn't we? So as I'm interested in the forces on the pulley, I don't care about the string either side of those dotted lines. Can you see? Now I want the force on the pulley, so force on pulley, being acted on by those two tension forces. So what we're saying is that the force itself must be having some reaction here, so RP, which levels out the two tensions. Otherwise the pulley would just fall down, wouldn't it? Right? So what is this R here, in other words? Well, it always helps to get rid of your pulley basically and just have it as a point um, instead, so you can see things better. So here's T, here's T. We have our normal reaction, because like I say, if this is a particle, this is a tangent, and therefore it's going to be kind of 90, it's going to be perpendicular to the corner, and therefore this force will always, so the force on the pulley will always bisect the two tension forces. Okay, it's always going to go down the middle between the two, isn't it? Because otherwise it's going to lean to one side. So the force going up here from the pulley must be the same as the forces going down enacted by these two tensions. Can you see? This is a 90-degree angle. It bisects the angle, so therefore this is 45 degrees. 45 degrees, right? If this was a right-angled triangle, you can see that the sine elements would go off here. There's the right angle. Yeah? So the force in play is this one here, which is the one next to the angle. So this is cos. Can you see? Cos 45 is the force that I want, the component that I want, which is x, over the hypotenuse, which is t. So therefore, that x must be t cos 45. Can you see? And this one here is also next to the angle, so this one must be t cos 45 as well. So if we resolve in line with the pulley, we got the force RP minus t cos 45 for one part of the string, but also the other part of the string as well. And this equals 0 as it's in equilibrium. So RP is 2t cos 45. We know what t is, or do we? I don't think we've worked out tension yet, have we? No, didn't say find the tension in the string, but we can find out the tension in the string quite quickly if we isolate this section here, yeah? So if we, at B, just do this to the side over here. At B, if we resolve down, we have our 0.8 G. Subtract tension, it's our mass 0.8, and then times that by A, and we know that A is 5.88 So therefore tension is going to be our 0.8 G subtract. So just moving that over, subtract 0.8 times 5.88, and that is 3.136 newtons to 3 dp. But you know, we would normally make that to less sig fig, but as we want to be exact here, I'm going to keep that value, so that's 3.136, and therefore 2 answer times cos 45 makes the force on the pulley 4.3 newtons to 3 SF. Okay, so how do you find the force on the pulley? The force on the pulley always bisects the two tensions, and therefore you just need to find out what these components are, because this lateral movement has no impact on the force of the pulley because they cancel each other out. Okay, that's that.